Welcome you all for this series of talks on Pedigree Polytopes. It's nice to see some of known faces in this audience. Some of you might not know what pedigrees are, or you might know pedigrees in relation to pets or pet food. I'm not going to talk about those, but it has to do something to do with genealogy, but in a different context. I will explain what pedigrees are first, and then say why we should be studying pedigrees, and then connect it to some important problems that are studied in combinatorial optimization. So with this brief introduction, I will also say a few words about myself. I am Tiru Arthanari. I have been working in this field of combinatorial optimization since I started doing research in 1965. With that brief introduction, I will also mention that recently I have published a book with the same name, Pedigree Polytopes, which will explain what I'm going to deliver through this series of lectures. This is an introduction which tries to bring in the connection between efficiency and polytopes. See, here when I say efficiency, it's about computational efficiency. How studies of polytopes are helpful in trying to devise algorithms that are efficient in the sense that they are easy to solve rather than which will be requiring enormous amount of time to solve the problem. So some combinatorial problems, as I mentioned earlier, are difficult problems. So far, we only have, the efficiency has not been proved that we can solve such problem easily. So with this introduction, I will try to explain why we study pedigrees. There are lots of reasons. They are beautiful objects, and many stalwarts in the field have appreciated the beauty of that and written many books. But we are not going to be studying polytopes for the beauty of them, but we have a purpose. We want to study optimization over polytopes. Polytopes are like, the objects which you are familiar with, like a box. You can see that it has sides, which we call them facets, and it has got corners, which we call them vertex. Then you may be able to travel along these edges from one vertex to the other. These are all known ideas about polytope. I assume you have some familiarity with these things. And if not, I will always suggest to you to go and find relevant material, easy to access. Some of the polytopes which are interesting for us are called 0-1 polytopes. What it means is that the vertices of these polytopes have only zeros and ones in them, and no other numbers will be there in describing the vertices of that. So among the 0-1 polytopes, we are going to study the pedigree polytope, which is also going to be a 0-1 polytope. And similarly, the other combinatorial objects can give rise to similar 0-1 polytopes. Actually, even though I said I will talk about what is pedigree, I will just give a brief sketch of what's going to be covered. First module in today's lecture, I'm going to cover what are pedigrees. Then I will go to explain what is the motivation for defining such an object. And this also will connect an important problem in combinatorial optimization, that is the symmetric traveling salesman problem. The next module, we will talk about some of the properties of the pedigree polytope. One is that we will discuss the dimension of this pedigree polytope. The next module, we will consider the adjacency testing of pedigree polytope. This is equal, the problem is like that. The given two vertices of the polytope, are they adjacent? In the sense there is an edge connecting them. That means you can travel along the edge to reach that. Not through the polytope, but along the edge. That's what is testing whether two pedigrees are adjacent or not. Next, we will show that the pedigree polytope is a special kind of polytope called combinatorial polytope. I will explain the definition, etc., in that module. And the most important step is that characterizing the pedigree polytope and then studying the membership problem in the pedigree polytope. Once that is done, we will be in a position to show that the difficult problem, like traveling salesman problem, can be, theoretically we can show that can be solved efficiently. So this will be done in the next module, and the last module will try to bring things together and say what are the possibilities that are there for doing research further. Now we are in a position to define what are pedigrees. This is the first module, as I said. Suppose we are given a number greater than 3, a number means 3, 4, 5, 6, like that, some number. We can talk about the number 1, 2, 3, 4, etc. That are our given vertices. The vertices are being numbered 1, 2, 3, like that. Then any two of these vertices, or you can say, we can talk about an edge. That is, suppose vertex I and vertex j we are given, then ij is a edge for our, we can call that an edge. Of course, right now I don't have to, this could be in general true, which can be used in graphs or any other areas where we study. But whenever you take two of the vertices and if it's connected in that graph, we say that's an edge. So that's the idea for calling this thing edge. Now, I'm going to introduce slightly in the next step, we can say, it's a triangle. Instead of just ij, suppose you also have k, ij, k, that means you are taking 3 of the vertices and putting them in that set, that is ij, k. That will be a triplet because there are 3 things in that, or a triangle, okay? So we will be dealing with triangles in defining pedigrees. So we can actually talk about triangles. For instance, when you have n equal to 3, you have only one triangle, 1, 2, 3. Is that correct? Yeah. So if you have 4, n equal to 4, then you can have 1, 2, 4, 1, 3, 4, or 2, 3, 4. Now these are the only triangles possible if you have n equal to 4. So together with the triangle for 1, 2, 3 and 4, we have all these things, 1, 2, 3 and 1, 2, 4, 1, 3, 4 and 2, 3, 4. Okay? So if that is clear, of course I can introduce a notation that capital delta power k is the set of all triangles for a given k. That means all possible those triplets that you can make given one k. And capital delta superscript a square bracket, within a square bracket you have k, then it means all those triangles up to k. That means for 3, 4, etc., k minus 1 up to k, whatever triangles that are possible, they are all put together in that set. So with that, of course, I can give some examples which I already talked about. For example, delta phi is equal to 125, 135, 235, 145, and 245, and 345. So you can have a look at the other definition of delta square bracket 4. And that of course includes, because up to 4, so it includes 1, 2, 3, 1, 2, 4, 1, 3, 4, and 2, 3, 4. Next, we can of course simply write delta square bracket n is just delta if you know which n we are talking about. The next I'm going to define the concept of a generators of a triangle. Given a triangle IJK, we define the generators of IJK, or the set of generators of IJK, as follows. If IJ is either 1, 2, 1, 3 or 2, 3, then the generator of IJK is just 1, 2, 3. That is the only generator. Otherwise, that is, if ij is not a subset of 1, 2, 3, then all these triangles which are like Rij, where R is less than I, greater than or equal to 1, and where S is between I and J, that is, S is greater than I, less than J, these triangles together form the set of generators of ijk. Ij is also called the common facet between the generator and the triangle. Sure, you have gone through the examples to understand what we mean by the set of generators of a triangle. You would notice that the generators of V, ijk, is same for all k greater than or equal to j plus 1. Notice that every generator of V has j in it. So we can define the set of generators of an edge as follows. This is the set of all edges Ri, where R is less than I, greater than or equal to 1, and Is, I is less than S, less than J. So this definition for generators of an edge would be used later in our discussions as well. I may have to give some more definition before I finally define pedigree. Pardon me for going through sequence of definitions. A collection of triangles is called a represent if it has one from each of the delta case for k equal to 3, 4, etc. And we call that represent minimal if it has exactly one from each of the triangles. Okay, so now we can define our main object, namely a pedigree. Next we shall define a directed graph D, where the delta, that means the set of all triangles for a given n, is our vertices, and the arcs in that directed graph are like this. U, V, two triangles, we connect if U is the generator of V. That's all. That gives us the directed graph. So there will be an arc from U to V if U is the generator of V. So now consider a spanning set in D called a pedigree. We call that if and only if it's a tree rooted in 1, 2, 3, because 1, 2, 3 is one of the triangles which is available. That's in delta, and that has no generator. That's our root. And exactly one element from each delta k equal to 3 to n is taken. So the number of elements in P is n minus 2, and every element of P other than the root has a generator in P. And the common edges are all distinct. So the 2 points that we have to notice is that it's a represent, and secondly, excepting for the root node, every other vertex in this set has a generator, and the common edges are all different. So these are important. The most important, I would say that the common edges are all distinct is very important. And a pedigree is a minimal represent because we take only one from each of the delta k. And it is a tree, so rooted in 1, 2, 3 implies that, of course, it doesn't have a generator, so that's the reason. And other triangles in P must have generators. Otherwise, it's not a tree because there will not be connection. And thus, the crucial condition is the common edges are different. And we will be making use of this to define pedigree in a different way as well later. Now that I have given you the formal definition of a pedigree, I would like to check that you have grasped it right. So with that in mind, I have created a set of 6 simple exercises. Please go through that, and once you have done, you can have a look at the answers Then we can move on to the next portion of this lecture. Thank you. Okay, are you trying the exercises? I find some are you not busy? Okay, to quick start. So let's look at the solution for B. We have 1, 2, 3, and we also have 2, 3, 4. So the 2, 3 is a common edge. So we do have a pedigree there for 4. Now 1, 3, 5 is another triangle that we have. So 1, 3 is common between 1, 2, 3 and 1, 3, 5. So that also now gives you a pedigree for 5. Finally, 1, 2, 6. 1, 2 is the common edge. So we do have a pedigree for 6. So please do the other exercises and check your answers next time when we meet.